Thank you for coming to my presentation. My name is Cvetomir Dimov. I'm a cognitive psychologist at the University of Geneva, and today I'll be talking about how I studied planning with a novel video game. This project has been a mix of cognitive psychology, UI design, computational geometry, and data analysis. In what follows, I will tell you why we study problem solving in the first place. Then I'll present to you Tick Tick, which is the novel video game that we created to study problem solving. Then I will talk to you about how we create problems in this video game and present to you a program that I wrote to find solutions to these problems. Then I'll specifically focus on planning and what the goals of this project are before I move to the two studies that I run to study planning. And finally, I will conclude. So problem solving, what is it? Whenever we have a goal and we don't know how to reach it, we rely on our problem solving abilities. And problem solving is really something that we engage in on a daily basis. Perhaps stereotypical examples of problem solving are trying to solve math problems or logical puzzles. But problem solving is much more. We solve problems when we create the shopping list for the week or when we do the actual shopping. We solve problems when we buy a car and so on and so forth. Problem solving is really part of our day-to-day life. To study problem solving, we designed a new game called Tick Tick. Here you're about to see a video of Tick Tick in a second, but here you can see the main elements of Tick Tick. There is a fireball on the screen and an ice cube, which are the two characters that the human controls. The goal is that the characters reach a target destination, in this case an open fire circle and an open ice square. To reach these target destinations, the two characters need to help each other. The fireball needs to block the fire rays and the ice cube needs to block the ice rays. So let me demonstrate to you how this works. So to solve this level, first the fireball is going to move up and block the fire ray. Then the ice cube can move to the second ice ray and block it so that the fireball can move through. Then the ice cube needs to move and block the other ice ray. And finally, it can block the first ice ray again to let the fireball through. Before the fireball reaches its target destination, it needs to block the fire ray again so that the ice cube goes back to its initial location. And now the ice cube can move to the target location, as can the fireball. And voila, this is the game. As you can see, this is a conceptually relatively simple game, but it allows us to create problems of various complexity. So on the right hand side is the problem that I just demonstrated to you. It consists of two ice rays and two fire rays that are crossing each other at multiple locations, and this results in a relatively complex problem. On the left hand side, we have a much simpler problem. Not only does it have fewer rays, but also these rays don't intersect. And in this specific problem, you just need one blockage to go to your target location. So perhaps these two examples demonstrate to you what factors affect problem difficulty. These are how many barriers we have and how many places these barriers intersect, and of course the start and goal locations of the characters. Now I would like you to think how we can design an algorithm that can solve these levels. Just take a few seconds, think about how to represent this problem. Okay, now I will move to presenting to you the problem solver, which is a program that I wrote to find solutions to these levels. This is the level creator and level solver. It's a little program that I wrote to find solutions to various levels in the game. It is much less beautiful than the actual game. In a sense, it allows us to create sketches of levels, but it has the advantage that it can then find solutions to those levels, which can substantially speed up the level creation problem. We can change the locations of the two characters, of the ice cube and of the fireball. We can equally change their target destinations. And we can also add rays, as many as we want to, of the two kinds, ice rays and fire rays. We can also remove the rays if we don't like the current version of the level. So let us start by creating a simple level. Let us add a fire ray here, another fire ray here, and an ice ray here. And let us also set the target location of the ice cube here and the target location of the fireball here. When we press solve, the solver identifies different regions and then finds all possible paths that the characters can take between these regions, and also finds the optimal path. The optimal path is the one that takes the fewer number of blockages. So here, for example, we know that there are two ice faces in this level. There are 4 fire faces. The optimal path has 3 moves, and there are in total 3 paths that are optimal, including some other statistics. How does this work? Let me briefly sketch out for you. So this is a sketch of the level that I just presented to you. In black is the level border, the 2 fire rays are in orange, and the ice ray is in blue. The level solver first identifies the regions that the rays partition the playing field in, after which it looks for all possible paths between these regions. So from the perspective of the fireball, the fire rays don't matter. The fireball can freely cross them, and the only real obstacle that it has is the ice ray. So from the fireball's perspective, the level really looks like this. From the fireball's perspective, there's just one ray that it cannot cross without the ice cube's help. Otherwise, it can freely move inside of this region and freely move inside of this region. Once it has moved to this region, nothing stops it to reaching its target location, so its job is done. Similarly, from the ice cube's perspective, ice rays are not an obstacle, and the only thing that matters are these fire rays. So the ice cube has the choice of moving between these 4 regions that the fire rays have split the playing field into. And its goal is really to move to this region down here with the help of the fireball. How does the algorithm identify these regions? Well, first it doubles every ray inside the playing field, and it also pretends that the outer border of the playing field is one big ray. It then splits rays whenever they intersect. So this is how it looks like. This is how the playing field looks from the perspective of the algorithm after it has doubled the ray that is inside of the playing field, and after it has segmented every ray at the points of intersection. The next step is to pick a point randomly, and starting this point, to pick the segment that is the most counterclockwise. So there's only one segment starting from this point, this one. So we just pick this one and we take its end as the next starting point. Then from this starting point, there are 2 rays coming out. There's this one and this one. The most counterclockwise is this one. So we continue with that. It ends at this point here. From this point, there's just one single segment starting. Again, there is one segment starting from this point. This last segment, it ends at our starting point. The fact that the end of the last segment is the same as the beginning of the first segment means that we have completed our phase. So this is our first phase. We can repeat the same procedure starting from the next remaining point. So there is a segment starting here. There's also just one segment starting from this point. And finally, the last segment ends where the first segment starts, which means that we have completed the phase. We can repeat the exact same procedure for the ice cube. Just as for the fireball, we can pick a random point to start at, and then continue selecting the most counterclockwise segment starting from this point. So this will bring us to this point, then to this point, and finally to this point. I think we have already understood the main idea behind the algorithm. So now we have identified the phases in which the playing field is split by the rays. These phases are the states which the fireball and the ice cube respectively can take. And the combined state is the state that the fireball is in and the state that the ice cube is in. Finding a solution to a level is performed by searching exhaustively through this state space. There is a little trick that the algorithm uses to avoid repeating the same computations over and over again. Namely, the algorithms first find all neighboring faces of a phase before searching exhaustively. This is very similar to Dijkstra's algorithm. Then once it searches all paths exhaustively, the algorithm identifies the path that requires the minimum number of moves, and it also counts the total number of paths available in this task. So to summarize, the program solver takes as an input fire and ice barriers, as well as start and target locations of characters. Then it identifies the segments that intersecting rays are split into. Then, based on all segments, it separates the playing field into fire regions and ice regions. And these jointly specify the problem space. Then it identifies all possible moves for each state and saves them in order to avoid recomputing them later on during search. Then it searches all possible paths exhaustively. Importantly, the algorithm is not allowed to visit the same state twice, because that would lead to infinite loops. Once it has computed all possible paths, which we call the search space, it identifies the shortest paths among these, which is the optimal solution. It computes the length of that solution, which we call the optimal solution length. Next, it counts the total number of paths inside of the search space, which we call the search space size. And finally, it visualizes all accessible states and all possible moves between them. And now I'll present to you some research that focuses specifically on planning and how we used these levels in this task to study planning. So planning is one way to solve problems. It is the process of formulating an abstract sequence of operations towards some goal. However, we don't always use planning to solve problems. In one of the examples of problem solving that I mentioned earlier, namely solving math problems, we don't typically solve through planning. In fact, often in class we study procedures on how to solve different types of problems, and we merely apply these procedures without planning in advance. What is interesting is that people seem to construct plans more or less systematically in different tasks, and we currently don't fully understand what determines how we construct these plans. The research presented here adds some additional data towards that question. Specifically, the project has the following three goals. First, we would like to identify how we can incentivize more planning in this task. Second, we'd like to create a problem set which is within the abilities of the general population, a problem set that varies systematically in difficulty, and a problem set that takes a reasonable amount of time to complete, which is about an hour. We'd like to also better understand what makes these problems difficult. And specifically, we would like to identify problem parameters that determine problem difficulty in this task. In study one, we wanted to pilot the task. We created a problem set by systematically varying the two parameters that we thought would influence problem difficulty, optimal solution length, or what is the minimum number of blockages needed to solve a level, and the search space size, which is the total number of paths in this problem. Importantly, all problems had only one optimal solution. This problem set consisted of 29 problems, of which 9 were warm-up and 20 were the main problems. 46 subjects participated in this study, which were recruited online. They went through an extensive tutorial, which explained the game, and then tried to solve each of the 29 problems. This study took about an hour and a half to complete, so rather on the long side. And importantly, when trying to solve each of the 29 problems, participants could see what is the optimal solution length on top of the screen, and also what is the blockage limit. In this case, it was 10 times the optimal solution length, so rather large. So if, for example, a problem needed 2 blockages to solve optimally, participants had 20 blockages at their disposal to solve the problem. We try to incentivize planning by providing participants a larger bonus if they solve the problem optimally. So they received 1 bonus point whenever they found the correct solution, but 3 bonus points if they found the optimal solution. This is how subjects performed in this task. Each dot corresponds to a subject. On the x-axis, we're plotting how many problems that subject solved, and on the y-axis, we're plotting how many problems the subject solved optimally. And as you can see, there are huge individual differences. So for example, this subject solved 7 problems and 2 of them optimally, whereas this subject solved 29 problems and 23 of them optimally. Importantly, there was a high dropout rate. Most subjects quit when they couldn't find the solution to a problem after a very long time. So for example, this subject solved 7 problems, which means that on problem number 8, they probably got frustrated and they quit. Similarly, this subject solved 25 problems, which means that they probably quit on problem 26, and so on and so forth. Overall, about half of subjects attempted all problems. So about half of subjects quit before attempting all problems. Another important point is that there were large individual differences in how optimal participants solve these problems. So this subject solved all 29 problems, but only 2 of them optimally, despite our incentivization scheme. And this one, on the other hand, solved over 20 problems optimally. And we can see these differences on the entire graph. Now let us try to look at problem difficulty. Here, each dot represents a problem. So each dot is an average over all subjects. On the x-axis, we are plotting how long participants typically needed to solve a problem. And on the y-axis, we are plotting what fraction of participants solved that problem optimally. So for example, this problem needed typically 39 seconds to solve and was solved optimally by 82% of subjects. This problem, on the other hand, needed about 176 seconds to solve typically and was solved optimally by 17% of subjects. What we can see is that these problems vary widely along these 2 measures. So some problems take 20 seconds, others take 220 seconds. Some problems are solved optimally in 5% of the cases, others solved optimally in 93% of the cases. But importantly, these 2 measures are strongly correlated, so that problems that take longer to solve are also less likely to be solved optimally. So both of these measures are indicators of problem difficulty. From now on, we're going to use optimal solution rate as our measure of problem difficulty. Both predictors that we hypothesized would correlate with problem difficulty. So the fraction of subjects that solved the problem accurately indeed correlated with problem difficulty. So the optimal solution length, which is the number of blockages in the optimal solution, correlated minus 0.67, and the search space size correlated minus 0.64. But importantly, we also found another measure, which we call the truncated search space size, that correlates even more strongly. So the truncated search space size is the size of the search space if all paths were truncated up to the length of the optimal solution. So if the optimal solution took 3 blockages, we would take all possible paths and cut them so that they're of length 3, and then we would count the number of unique ones. This measure correlated even more strongly. But importantly, we also ran a stepwise logistic regression in which only the optimal solution length and the truncated search space size remain significant, and they accounted for about 63% of the variance in problem difficulty. So to conclude, there was a high dropout rate, there were large individual differences in performance on this problem set in TickTick. We generally found the problem set to be within subjects' abilities, but a little bit more difficult than we desired. And finally, we identified a new predictor that, together with optimal solution length, could explain a large portion of what makes a problem difficult. In study 2, we wanted to solve some of the issues we had with study 1. First, we introduced a time limit to reduce the dropout rate. Second, we decreased the blockage limit to the optimal solution length plus 2. So now, if a problem needed 3 blockages to be solved, participants had at most 5 blockages to find a solution, otherwise they would receive 0 points. Next, we made problems easier because we found the previous problems a little bit difficult. And finally, we systematically varied optimal solution rate and the new variable that we found, the truncated search space size. In this study, we reduced the number of problems. The result was a study that took about an hour to complete. And as before, we provided both optimal solution length and the blockage limit and gave participants a higher bonus if they solved the problem optimally. Our modifications were successful. First, many more subjects completed all problems, so the dropout rate was reduced significantly, 36 out of the 43 subjects. There was a much stronger correlation between the number of problems solved and those solved optimally. And moreover, problems that were solved were typically solved optimally. Importantly, the number of problems that were solved optimally were about 50%. So on average, a subject in our study could solve about half of our problems optimally. But as you can see, there are large individual differences. The typical subject solved between 20 and 80% of problems optimally. In terms of the predictors of problem difficulty, all 3 variables correlated strongly with optimal solution rate. Search space size correlated the least. A stepwise logistic regression left only the optimal solution length and the truncated search space size as the 2 significant variables, which accounted for a little over half of the variance in problem difficulty. So we replicated the results from the previous study. Now to summarize, I presented TickTick, which is a simple problem-solving video games that has the potential to create problems of various difficulty, even very difficult ones. I developed TickTick Solver, which can find solutions to TickTick problems and characterize them along several dimensions. Then we introduced a blockage limit in our studies to incentivize participants to plan. And importantly, this blockage limit had to be quite tight so that participants are forced to try to find the optimal solution and hence plan more. On the pragmatic side, We had a high dropout rate in study 1, which we reduced by introducing a time limit. Importantly, we also found how we can create more difficult problems, namely by varying the optimal solution length and the size of the truncated search space. And finally, I would like to make a shout out to several software projects that were indispensable in this research project. First is the closure library Quill, that is at the heart of the TickTick solver. Second is the notch stack, and specifically Clay, which I use for my analysis notebook and for this presentation. Tablecloth, which I use for my data analysis. FastMath, which is a library that I use for computing correlations for running the logistic regression. And finally, Tablecloth, which I use for some of the visualizations in this presentation. I would also like to take the R to thank the R programming language. Thank you for your attention.